All right, continuing our discussion of electrochemistry, we're going to talk about what are standard cell potentials and how do we calculate them. Is the potential energy difference between the anode and the cathode, and it's represented by E0 or E naught. And the units on this are in volts. And so the higher the cell potential, the more work we can do with this redox reaction. And so the electrons would rather go from a higher potential energy to a lower potential energy. And if we can force them to go through a wire, then we can use that electric current to do work. Now, we talk about half reactions, but in reality, we really can't have half a reaction. We can't have reduction without oxidation and vice versa. But it's convenient to think about redox reactions in this way. And much like we did with standard enthalpies of formation and standard free energies of formation, what we do is we define a standard half reaction that we measure everything else with respect to. And that standard half reaction that we measure every other half reaction with respect to so that we can have this idea of half reactions is called the standard hydrogen electrode. And so this reaction is the reaction for the standard hydrogen electrode. So it is not real that the cell potential for this reaction, for this half reaction, is zero. We just set it to be zero. So we say that for the conversion of 2 hydrogen ions into 1 mole of hydrogen gas, we say that the cell potential for this half reaction is going to be zero. And so then whichever direction we run it in, that's going to be zero. And so then we measure and report all other half reactions relative to this half reaction. And so this isn't really real, but it's a convenient way of bookkeeping and seeing how do the cell potentials for different half reactions compare to one another. Okay, so by defining this standard hydrogen electrode, we can measure everything else with respect to this. And by defining that hydrogen electrode to be zero, then we can talk about what is the cell potential of any other half reaction. And we call that the half cell potential. And the standard half cell potential just means we're at standard conditions, right? And so critically for most of these electrochemical reactions, that means that everything that's in solution is 1 molar. And if we have gases, that means that their partial pressure is 1 atmosphere. And you'll see tables of these half cell potentials. And by convention, we always write them as reductions. And so they'll always be written as having electrons on the reactant side. And so we add electrons to something to cause a reduction. And so just as an example, the half cell potential for the reduction of zinc 2 to neutral zinc has a half cell potential of minus 0.76 volts. But of course, when we have an actual reaction, we have a reduction and an oxidation. And so this is reduction. This is the same reaction, but in the reverse is now an oxidation. If we reverse the reaction, then just like delta G, delta H, delta S, all we have to do is change the sign. So when the reaction runs in this direction, the half cell potential is minus 0.76 volts. When the same reaction runs in the opposite direction, then the cell potential is positive 0.76 volts. All right, so if I wanted to calculate the cell potential for this reaction, what I would do is I would go to one of those tables and look up the cell potentials for each of the half reactions. Now they're all going to be written as reductions. So one of them is going to be written in the correct direction, and the other cell potential that I look up is going to be backwards. Right? So in this case, the reaction I'm actually interested in is copper 2 going to copper. And so this half cell reaction is in the proper direction, but this one is backwards. And so I'll have to reverse it when I want to calculate the cell potential. And so formally, to calculate the cell potential, we would do the cell potential of the cathode and then minus the anode, because the anode is where oxidation takes place. And so when I look up the E0 cell, it's going to be for the reduction, and so I have to reverse it. In reality, I don't actually think about it this way, right? I just look at the reaction I'm given, look at the half reactions that I find, and the one that is going in the proper direction, so in this case, copper 2 plus going to copper, that's what I want, copper 2 plus going to copper. So I'll leave this one alone. I won't change the sign of the half cell potential, but the zinc one is going backwards, right? I'm starting with zinc metal, not zinc 2 plus, so I know I need to reverse this reaction, so that's the one I need to change the sign on. So if you like it this way, that's perfectly fine. But I don't ever think about it this way. I just say, okay, the one that's going in the direction I want, I'll leave it alone. The one that's going backwards in the reaction I actually want, that's the one I'll change the sign of. So if I was calculating E0 cell for that reaction, I would do, right, this one's going the right way, so I'll leave its sign alone. This one is actually going in the opposite in the reaction I'm interested in, so I'll change the sign. So instead of being negative 0.76, it'll be positive 0.76. And so the E0 cell for that reaction is 1.10 volts. Now, one important thing to point out that's different between delta G and delta H and delta S is that the cell potentials are intensive properties. It doesn't matter what the stoichiometry is. And so if this reaction had to have been run twice, so if I really had 2 Cu2 plus going to 2 Cu, it doesn't matter. The cell potential wouldn't change. And we'll see that in some of the examples that we do. All right, so this is just a reminder that we have two types of electrochemical cells. We have voltaic cells that are spontaneous. And so it turns out going from zinc metal to zinc 2 plus and then copper 2 plus going to copper, the electrons going in this direction is spontaneous. And for voltaic cells or galvanic cells, the E0 is positive. That reaction can be run in reverse, just like any chemical reaction. In this case, it would be called an electrolytic cell. So in this case, we're getting electricity out. In this case, we're putting electricity in. If I want the reaction to run backwards, then E0 cell is going to be negative. So galvanic cells have positive E0s and they're spontaneous. Electrolytic cells are not spontaneous and they have negative E0s. All right, so when you go to look up these half cell potentials, you usually see these giant tables. And the table that we're seeing here is just a subset of a much larger table. But you can see that all of the reactions are written as reductions. So the electrons are always on the left-hand side. And they're usually written such that the half cells that have the most positive potentials are at the top, and then they're written in decreasing cell potentials. So they get more negative as we go down. And when we do it this way, the reagents that we have over here, these tend to be very strong oxidizing agents. So remember that if something is easily reduced, that means that it's going to be good at oxidizing something else. So the electrons that the fluorine is taking, it must be stealing from something else. So when you look at these charts, the reactants at the top of the table are going to be strong oxidizing agents. But as these cell potentials get less positive, they become less spontaneous. And so they're less likely to happen. And they'll go from being positive to even negative. And so then the reagents that we have on the product side at the low parts of the table, these are going to be strong reducing agents. And so the further down in the table that we are, the better the reducing agent it's going to be. And so the more that the reaction wants to run in the opposite direction. All right, so to finish off this video, we're going to do a couple examples of calculating cell potentials. But with the software I use to make these videos, it's a little bit hard for me to pull up those giant tables and scroll through them. So what I'm going to recommend that you do is pause the video and then go to OpenStax or whatever textbook that you use. There should be a big table of these cell potentials at the end of that textbook, or just Google table of cell potentials and see if you can find the relevant half cell potentials that we need to calculate this reaction. So pause this video and see if you can find the two cell potentials. And then once you've found them, go ahead and restart and we can continue on with this problem. Okay, so I went through and found the cell potentials that I think are relevant. And so the two that I found are Pb2 plus 2 electrons goes to neutral lead. And the E0 that I found for that is negative 0.13. And then the other one that I found is Ni2 plus 2 electrons goes to neutral nickel. And the E0 for that one was negative 0.23. All right, so now to calculate the standard cell potential, what I typically do is I don't worry about what's the anode and what's the cathode. I just look at which directions are running in the correct directions. So in this reaction that I'm trying to calculate the cell potential for, I'm going from nickel 2 plus to neutral nickel. So this one is going in the correct direction. So when I add up the cell potentials, I'll keep that sign the same. So it's minus 0.23. And then one of them is always going to be in the right direction and one's going to be in the wrong direction. And so the one that's in the wrong direction is this one, right? This cell potential is for lead 2 going to lead, but I want it going in the opposite direction. So I need to change the sign. So when I add up the cell potentials for the two half reactions, this sign needs to change. And so instead of adding negative 0.13, I'm going to add positive 0.13. So the cell potential is going to be negative 0.10 volts. And I'm sorry, I should put the units on here. These should both be in volts. All right, so that is the cell potential. And then the final question, is this a galvanic or electrolytic cell? So galvanic cells have a positive E0 and they're spontaneous. Electrolytic cells have a negative E0 and they're not spontaneous. And so in this case, since my E0 is negative, this is a non-spontaneous electrolytic cell. Okay, so here's another example. And again, I would encourage you, pause the video and then go see if you can look up in your table of cell potentials and see if you can find the two relevant half cell potentials. Okay, so for the ones that I found are and the half cell potential for that one is positive 1.09 volts. And then the other one I found is Ag plus an electron and the E0 for that one is 0.80 volts. And so now for the E0 cell, I need to add these together, but I'm going to have to flip one. And so the Br2 going to 2Br minus, that's the one going in the correct direction. So I'll leave that sign alone. So I have positive 1.09. But then this one is going in the wrong direction. But as I mentioned earlier, the stoichiometry doesn't matter. It doesn't matter that the actual reaction is 2 silvers going to 2 silver plus. Since the cell potentials are intensive properties, the stoichiometry doesn't matter. And so whether there's 1 silver or 2 silvers, the cell potential is the same. But since this one's running backwards from the way I want it in the actual reaction, when I add them together, I need to change the sign. So I'll do minus 0.80. And so then the cell potential is 0.29 volts. All right, and then since this is positive, it means it's spontaneous, and this is a galvanic cell. Okay, last example. So again, I'd recommend pause the video, see if you can find the cell potentials, and then go ahead and restart the video, and we can continue from there. All right, so the cell potentials I found are as follows. All right, and then the aluminum reaction is going in the wrong direction, right? I really want aluminum going to aluminum 3 plus. So when I calculate the cell potential, I need to flip that first one. So instead of negative 1.66, it's going to be positive 1.66. And so then that means that this one is going in the correct direction. I'm going from NO3 minus to uh, nitrogen monoxide. And so I'll leave that cell potential alone. And then so I get 2.66 volts for that cell potential.